Welcome. This video is going to look at average atomic mass number, what it means, and how to calculate it. Average atomic mass is defined as the weighted average mass of the isotopes of that element. And it's different from the mass number because it represents all the isotopes known for that element. Remember, mass number is talking about one specific atom. And because elements have isotopes that are lighter or heavier than each other, each atom can have its own unique mass number. But average atomic mass is looking what's the average mass for all the isotopes as we find that particular element in nature. So isotopes occur in nature in different amounts, not equal amounts, and that's called percent abundance. So that means your atomic mass has to be what we call a weighted average of all the isotopes for that element. So your sample size is always 100 or 100%. So that's why the mass on periodic tables always have decimals to them, is because it's an average. So how do we find the average? You take the percent abundance for any isotope times the mass known for that isotope, and you do that for every isotope you have, and you add them up. So for more than 2 isotopes, that my formula here just shows 2 isotopes. If you had more than 2 isotopes, you just continue with this same process. Percent abundance times mass. And you can give the percent abundance as a decimal, or you can put the whole percent over 100. And I'll show you what I mean by this. But the mass of the isotopes is really, it's the average of 100 atoms, or 100% of the sample. And you have to be careful when you're reading the problem. They may give you the mass in AMU, which are atomic mass units, and they're really, really small. It's nowhere near a gram. Or it may be in grams because they may be dealing with a much bigger sample. So just pay attention to your label and label your final answer accordingly. Look at some examples. Lithium has 2 isotopes. Lithium-6 has a mass of 6.015 AMU and is 7.5% abundant in nature. Lithium-7 has a mass of 7.016 AMU and is 92.5% abundant in nature. Find the average atomic mass for element X. And my hint says atomic mass is always a weighted average, so use the mass and abundance for each isotope in the formula. So I'm going to go ahead and go to another slide here and work through my solution. If you want to pause and try it on your own first, this would be a good place to pause the video, and then we'll look at the solution together. So when I read the problem, it told me that I have one isotope that weighs 6.015 AMU, and its abundance is 7.5%. I'm going to leave it as a percent, and I'm going to go ahead and add information about my second isotope, which is 7.016 AMU times 92.5%. You notice my percents add up to 100. That's good. And then I'm just going to divide the whole thing by 100%, or by my sample size. So this kind of looks like a typical average that we do. All of our parts, 7.5 and 92.5, divided by the total parts, 100. And this gives me an average atomic mass of 6.94 AMU. The other way to do it, and the way some of you maybe thought about doing it, and this is fine, you'll get the same number, is take the 6.015 AMU times, and now you go ahead and change your mass to, or change your percent to a decimal right away, times 0.075, and then 7.016 AMU times 0.925. And this works exactly the same. You will also get 6.94 AMU. The reason I prefer the first method is because with a decimal, oftentimes students want to divide by something. You're used to dividing to get an average. I mean, not a decimal, but with an average, you're used to dividing by some number at the end. So this lets you divide by a number, so you're not tempted to take this suddenly and divide by 2. And the other thing is when you have smaller percentages like 7.5, you don't have to worry about if you got the decimal moved properly or not. But as I said, either method will work just fine. So here's another example. It says, which isotope must be more abundant, copper 63 or copper 65? And my hint is, look at the average atomic mass given for copper on your periodic table. And when I look on the periodic table, I see copper is listed as having an average atomic mass of 63.55. Well, copper 63 and copper 65, if there was 50% of each, the average would be right in the middle, or 64. But this average isn't. So if I think of this as being a teeter-totter, if it was balanced between copper 63 and copper 65, the mass would be 64. But we are way over to the copper 63 side. So that tells me copper 63 must be much more abundant to move that average much closer to copper 63. You may remember the definition says that if you round off the average atomic mass, that will be the mass of your most abundant isotope. And the triad number 3 says an element has two naturally occurring isotopes, X14, X15. You've got the masses and the relative abundance. So this is very similar to the first one, except now you're asked to identify the unknown element. So I've added another hint here, and that is to look at the periodic table when you're done and find the element with the same or very similar average atomic mass. So again, if you want to pause and try this on your own, I would encourage you to do that. Otherwise, I'm going to go ahead and start working my solution on the next slide. So just like triad number 1, I'm going to take my 99.63% and leave it as a percent. And that means I can also take my 0.37% and leave it as a percent. And I'm going to multiply each one by the mass of the isotope that they are associated with. And then I'm going to divide the whole thing by 100. And when I plug this into my calculator, I am coming up with a mass of 14.00675905. So do I have to hold on to all those decimals? No. Our periodic table and many periodic tables round to the nearest 100th or possibly the 1000th. Nearest 100th is just fine for us. So that would round to 14.01 AMU. And when I start looking at the periodic table, I see that they go pretty close to increasing mass. And so I work my way across, and I see that that must be nitrogen with the symbol N.